Hello friends, during our discussion on electromagnetic waves in the previous lecture, we concluded that an electromagnetic wave exerts a force and a pressure on the surface and they are polarized if their electric field vectors are all in a single plane called the plane of oscillation. We also learned that when a polarizing sheet is placed in the path of light, only electric field components of the light parallel to the sheet's polarizing direction are transmitted by the sheet. Components perpendicular to the polarizing direction are absorbed. In today's lecture, we shall be studying the geometrical optics, which is an approximate treatment of light in which light waves are represented as straight line rays. Reflection and refraction. Although a light wave spreads as it moves away from its source, we can often approximate its travel as being in a straight line. The study of the properties of light waves under that approximation is called geometrical optics. For the rest of this discussion, we shall discuss the geometrical optics of visible light. The photograph here shows an example of light waves traveling in approximately straight lines. A narrow beam of light called the incident beam, angled downward from the left and traveling through air, encounters a plane, that is, a flat water surface. Part of the light is reflected by the surface, forming a beam directed upward towards the right, traveling as if the original beam had bounced from the surface. The rest of the light travels through the surface and into the water, forming a beam directed downward to the right. Because light can travel through it, the water is said to be transparent, that is, we can see through it. The travel of light through a surface that separates two media is called refraction, and the light is said to be refracted. Unless an incident beam of light is perpendicular to the surface, refraction changes the light's direction of travel. For this reason, the beam is said to be bent by the refraction. Note in figure that the bending occurs only at the surface within the water. The light travels in a straight line. In this figure, the beam of light in the photograph are represented with an incident ray, a reflected ray, and a refracted ray. Each ray is oriented with respect to a line called the normal, which is perpendicular to the surface at the point of reflection and refraction. Here, the angle of incidence is theta 1, the angle of refraction is theta prime 1, and the angle of refraction is theta 2, all measured relative to the normal. The plane consisting the incident ray and the normal is the plane of incidence, which is in the plane of the page. Experiment shows that reflection and refraction are governed by two laws. Law of reflection: a reflected ray lies in the plane of incidence and has an angle of reflection equal to the angle of incidence, both relative to the normal. In figure, this means that theta prime 1 is equal to theta 1. Law of refraction: a refracted ray lies in the plane of incidence and has an angle of refraction theta 2 that is related to the angle of theta 1 by n2 sine of theta 2 is equal to n1 sine of theta 1. Here, each of the symbols n1 and n2 is a dimensionless constant called the index of refraction, which is associated with the medium involved in the refraction. Chromatic dispersion. The index of refraction n encountered by light in any medium except vacuum depends on the wavelength of light. The dependence of n on wavelength implies that when a light beam consists of rays of different wavelengths, the rays will be refracted at different angles by a surface. That is, the light will be spread out by the refraction. This spreading of light is called chromatic dispersion, in which chromatic refers to the colors associated with the individual wavelengths and dispersion refers to the spreading of the light according to its wavelength or colors. Generally, the index of refraction of a given medium is greater for a shorter wavelength, corresponding to say blue light, than for a longer wavelength, say red light. As an example, figure shows how the index of refraction of fused quartz depends on the wavelength of light. Such dependence means that when a beam made up of waves of both blue and red light is refracted through a surface such as from air into quartz or vice versa, the blue component, the ray corresponding to the wave of blue light, bends more than the red component. A beam of white light consists of components of all the colors in the visible spectrum with approximately uniform intensities. When you see such a beam, you perceive white rather than the individual colors. In figure a beam of white light in air is incident on a glass surface. Because the color of screen is white, a beam of white light is represented with a gray ray here. Also, a beam of monochromatic light is generally represented with a red ray. Of the refracted light, only the red and blue components are shown. Because the blue component is bent more than the red component, the angle of refraction theta 2b for blue component is smaller than the angle of refraction theta 2r for the red component. In figure B, a ray of white light in glass is incident on a glass-air interface. Again, the blue component is bent more than the red component, but now theta 2b is greater than theta 2r. To increase the color separation, we can use a solid glass prism with a triangular cross section. The dispersion at the first surface is then enhanced by the dispersion at the second surface. Rainbow. The most charming example of chromatic dispersion is the rainbow, when sunlight consisting of all visible colors is intercepted by a falling raindrop. Some of the light refracts into the drop, reflects once from the drop's inner surface and then refracts out of the drop. Figure A shows the situation when the sun is on the horizon at the left and thus when the rays of sunlight are horizontal. The first refraction separates the sunlight into its component colors and the second refraction increases the separation. If many falling drops are brightly illuminated, you can see the separated colors they produce when the drops are at an angle of 42 degrees from the direction of the anti-solar point A, the point directly opposite the sun in your view. Because any drop at an angle of 42 degree in any direction from A can contribute to the rainbow is always a 42-degree circular arc around A, and the top of a rainbow is never more than 42 degree above the horizon. When the sun is above the horizon, the direction of A is below the horizon, and only a shorter, lower rainbow arc is possible. Because rainbows formed in this way involve one reflection of light inside each drop, they are often called primary rainbows. A secondary rainbow involves two reflections inside a drop as shown. Color appears in the secondary rainbow at an angle of 52 degree from the direction of A. A secondary rainbow is wider and dimmer than a primary rainbow and thus is more difficult to see. Also, the order of colors in a secondary rainbow is reversed from the order in primary rainbow. Rainbows involving 3 or 4 reflections occur in the direction of the sun and cannot be seen against the glare of sunshine in that part of the sky, but have been photographed with special techniques. Total internal reflection. The figure shows rays of monochromatic light from a source point S in glass incident on the interface between the glass and air. For a ray A, which is perpendicular to the surface, part of the light reflects at the interface and the rest travels through it with no change in direction. For rays B through E, which have progressively larger angles of incidence at the interface, there are also both reflection and refraction at the interface. As the angle of incidence increases, the angle of refraction increases. For a ray E, it is 90 degrees, which means that the refracted ray points directly along the interface. The angle of incidence giving the situation is called the critical angle theta c. For angles of incidence larger than theta c, such as for rays F and G, there is no refracted ray and all the light is reflected. This effect is called total internal reflection because all the light remains inside the glass. To find theta c, we use the law of refraction equation. N2 sine of theta 2 is equal to N1 sine of theta 1. We arbitrarily associate subscript 1 with the glass and subscript 2 with the air, and then we substitute theta c for theta 1 and 90 degrees for theta 2, which leads to N1 sine of theta c is equal to N2 sine of theta 90 degrees, which gives us theta c is equal to sine inverse N2 upon N1. Because the sine of an angle cannot exceed unity, N2 cannot exceed N1 in this equation. This restriction tells us that total internal reflection cannot occur when the incident light is in the medium of lower index of refraction. If source S were in the air, all its rays that are incident on the air glass interface, including F and G, would be both reflected and refracted at the interface. Total internal reflection has found many applications in medical technology. For example, a physician can view the interior of an artery of a patient by running two thin bundles of optical fibers through the chest wall and into an artery. Light introduced at the outer end of one bundle undergoes repeated total internal reflections within the fibers, so that even though the bundle provides a curved path, most of the light ends up exiting the other end and illuminating the interior of the artery. Some of the light reflected from the interior then comes back up the second bundle in a similar way to be detected and converted to an image on a monitor's screen for the physician to view. The physician can then perform a surgical procedure such as the placement of a stent. Polarization by reflection. You can vary the glare you see in sunlight that has been reflected from, say, water by looking through a polarizing sheet and then rotating the sheet's polarizing axis around your line of sight. You can do so because any light that is reflected from a surface is either fully or partially polarized by the reflection. Figure shows a ray of unpolarized light incident on a glass surface. Let us resolve the electric field vectors of the light into two components. The perpendicular components are perpendicular to the plane of incidence and thus also to the screen. These components are represented with dots as if we see the tips of the vectors. The parallel components are parallel to the plane of incidence and the page. They are represented with double-headed arrows. Because the light is unpolarized, the two components are of equal magnitude. In general, the reflected light also has both components but with unequal magnitudes. This means that the reflected light is partially polarized. The electric fields oscillating along one direction have greater amplitudes than those oscillating along other directions. However, when the light is incident at a particular incident angle called the Brewster angle theta b, the reflected light has only perpendicular components. The reflected light is then fully polarized perpendicular to the plane of incidence. The parallel components of the incident light do not disappear but refract into the glass. Brewster's law. For light incident at Brewster angle, we find experimentally that the reflected and refracted rays are perpendicular to each other. Because the reflected ray is reflected at the angle theta b and the refracted ray is at an angle theta r, we have theta b plus theta r is equal to 90 degree. The two angles can also be related with the law of reflection equation, arbitrarily assigning subscript to the material through which the incident and reflected rays travel. We have n1 sine of theta b is equal to n2 into sine of theta r. Combining these equations leads to n1 sine of theta b is equal to n2 sine of 90 degrees minus theta b, which is equal to n2 cos of theta b, which gives us theta b is equal to tan inverse n2 upon n1. Note carefully that the subscripts in equation A are not arbitrary because of our decision as to their meanings. If the incident and reflected rays travel in air, we can approximate n1 as a unity and let n represent n2 in order to write equation A as theta b is equal to tan inverse n, the simplified version of equation A known as Brewster's law. So here we come to the end of our discussion in this lecture and therefore we sum up. Geometrical optics is an approximate treatment of light in which light waves are represented as straight line rays. When a light ray encounters a boundary between two transparent media, a reflected ray and a refracted ray generally appear. A wave encountering a boundary across which the index of refraction decreases will experience total internal reflection if the angle of incidence exceeds a critical angle. A reflected wave will be fully polarized with its electric field vectors perpendicular to the plane of incidence if it strikes a boundary at the Brewster angle. So friends, that is it for today. See you in the next lecture where we shall be discussing more on electromagnetism. Thank you very much.